All right, so this lecture will be a bit different. This will be, I guess, maybe a little bit more speculative and just an overview of, I guess, yeah, things that I think are exciting happening in the field right now. Okay, so yeah, a lot of people ask sort of, yeah, what are the most exciting areas of deep RL research? So, should we be doing HRL, deep learning, deep RL for robotics, model-based RL? The field is moving really quickly, and in the age of archive, it's pretty hard to keep up. So, yeah, what kinds of things should we be working on? And I think basically in deep RL, you don't really have to worry. The field is really new. Everything is still exciting. One point I like to make is, like, literally nothing is solved yet. We saw ways of, how do you learn value functions? So it might not get a lot of people excited if you say, yeah, I'm working on learning value functions. Like, don't we know how to do that? But we'll see, actually, there's still cool fundamental stuff to be done. And the same goes for, say, policy gradients. The lectures we saw earlier today, especially John's lecture on sort of advanced policy gradients, there's still a lot to do. We're still figuring out how to do policy gradients better. So and this goes, yeah, for pretty much every method, technique, or part of a deep RL agent. And even deep learning itself, how do we train deep nets? There's still a lot of work to do. Like, we still don't know what's the right nonlinearity. Maybe this is getting too low level, but I think, yeah, it's important to remember to not get discouraged that, yeah, nothing is solved yet. It's all up for grabs. But then I guess, yeah, it would be a bit boring if I said, yeah, everything's interesting and finish the talk there. So if I had to pick two things, I think when we talk about a lot of, like, yeah, different techniques like HRL, model-based RL, the things that, yeah, I think the reasons we expect them to help come down to two things. One is data and sample efficiency. So this, I think, is one of the really exciting things about deep RL, that our methods are still so data inefficient that, like, there are multiple order of magnitude improvements that we still need to get to make this stuff really practical. So that's kind of exciting. And yeah, you can attack this problem in many different ways, and I'll talk about a few different ones. And the other one is exploration. I guess from the lectures we saw today, you might think, wow, the way we do explorations actually, like, seems really dumb. We just select, like, random actions. You, like, flip a coin and decide, should I take a good action or a random action? And the state of the art, like, hasn't gone that far beyond that. There's a lot of work on better exploration methods, but I think we're not quite there yet. And so it's still, do you add noise to your actions, or do you add noise to the parameters? Maybe this is the extent of yeah, progress in exploration. So there's a lot of really cool stuff to do there. So for the rest of the talk, I'll, I guess, look at papers that I think, recent papers that I think are really exciting, and mention a few things we've been working on. Yeah, it might seem a little bit biased towards work from DeepMind, but I know work of my colleagues probably better than the work of the rest of the field, and I think we'll see a lot of cool stuff from Berkeley and OpenAI people and others tomorrow. So yeah, the first thing I want to talk about is, I think, so this is one example of looking at fundamental problems and getting major impact from that. So specifically, yeah, learning value functions. So the value function gives us the expected future discounted return, either for a given state or if it's a Q function for a state in action. And here the key is that we're looking at the expected return. And I think, yeah, this came up in a few questions. So, what if there is variance? What if in one state you can get a small but positive reward, sort of with very high probability, but in another state you can maybe get a very high reward but with small probability. Which one should you prefer? And of course it depends. If you want to make sure that you get some reward, then probably you should pick the first one. So yeah, looking at expected values ignores the variance. That's one of the things. It also ignores multimodality, that maybe different things can happen. So you can maybe get a big reward or a smaller reward, and you don't know which one will happen. And how can you exploit this kind of information? Some recent work from Mark Belmar, Will Dabney, and Remy Munoz at DeepMind started looking at distributions, full distributions of returns instead of just expected returns. So it turns out that if we look at the Bellman equation, written in a slightly different form, so the Q value is essentially expected reward plus the expected Q value of the next state, where expectations here are over policies and environment dynamics. So if we want to model the full return, the full distribution of the return, then there's also a distributional form of the Bellman equation. So we'll use ZSA to basically represent the distribution of the return if you take action A in state S. And the distributional Bellman equation has a very similar form. So you will have the distribution of the reward you will get for taking action A in state S, arriving in state S prime. And here, so capital letters are showing random variables. So the return itself, the reward itself is random, and then the next state you end up in is also potentially random. And then, of course, the action you take in the next state is random. So the distribution of the return is this distribution plus the discounted distribution of the next state return. So the question is, this has been known for a long time actually, but how can you use this to get a better learning algorithm? So they came up with something they called C51. So it's a specific instantiation of using this idea in a Q learning agent. So the main change here is that now, instead of outputting Q values for each of the actions, now your network will output a full distribution for each action. So it will output the distribution of the Q value for each action. So how can you do this? So there are many ways of modeling distributions. The one they picked is to represent, or essentially represent it as a categorical distribution. So you're going to say, okay, I'm going to assume my returns are between -10 and 10. And this was applied to Atari, so this is a reasonable assumption because actions are still clipped. And now you're going to essentially break up this space of possible returns into 51 bins. You can read the paper for why 51. You can use fewer or more, but this specific one worked especially well. So now you have these 51 bins, and what your neural network will do is for each action in each bin, it will output the probability that the return has that value for this action. So we're going to call these quantities PXAs. So slight change of notation here, XT represents the state, so what we've been referring to as S. So you output these 51 numbers for each action. And then to compute the Q value, you just take a weighted sum. So basically, each of these bins represents the probability that the return has this specific value. So to get the Q value, you essentially take, again, the expectation, the expected return. So to do the actual Q learning, we're still, or to do the action selection, we're still looking at expected values. So you're still selecting the one with the highest value. But to do the actual learning, you now apply the distributional Bellman equation. So it looks complicated, but it's really not that different from the original Q learning. And the gist of it is, okay, how do you compute the target? Now, you don't just need a target for your Q value. You have to come up with the target distribution for your current state distribution. So the way it looks like is you're going to look at the next state distribution for the highest, for the value with the highest action. So you first compute the expected, the expected value for each action in the next state. You pick the action with the highest value, and then you take the distribution of the return for that action. And then you apply this distributional Bellman updates or operator. So the first thing to do is to contract it by gamma, so to apply the discount factor. So what this does is it essentially shrinks the bins towards 0. So that's fine, that's straightforward. And then you, since you're doing Q learning, you got an actual return, which you sampled from the environment. So all that does is just shift your distribution by the reward amount. And this will give you essentially both the locations of the bins and the probability for each of the bins. The tricky bit really is that these bins might not line up with the original bins that you had. So you had 51 bins from -10 to +10. So then you have to do a projection of the distribution you computed onto these 51 bins. And that's, I think, essentially linear interpolation here. But I think you could be more sophisticated about it. And then to do the actual learning, you just apply a cross-entropy, a cross-entropy update. So now it's essentially, it looks like supervised learning or classification, where you computed these bin weights MI, and that's the target for sort of all the bins for the key value you're trying to update. So now your network outputs full distributions, and you have a way of computing targets for full distributions, so you can do Q-learning and acting. So this is an example of an agent playing Space Invaders, and it's showing basically the distributions of the key values for the different actions. And you can see that, okay, they threw away the negative bins here because there are no negative rewards in Space Invaders. But you see the different colors represent different actions. So most of the time, the distributions for different actions are quite similar, except for key points where you have to make the important decisions. And you see that basically in some states, the network learns that it learns the probability that it will make a mistake and lose a life. So that's the weight it puts on the 0 rewards bin. So does this actually make a difference? Because we're still just selecting actions based on the highest expected key value, but now we're learning this distribution. And it turns out that this makes a huge difference. I think this work was the biggest improvement over DQN or in value-based methods that we've seen. So just doing, I think, this one specific change improves the performance of DQN on Atari, slightly improved version, from 79% median to 178%. And we see some of the improvements we looked at in lecture 3. So double DQN improved it by 40%, dueling was like 70%, prioritized dueling, which is basically a combination of a bunch of these techniques, only gets to 172%. And the C51 agent, so just doing the distributional Q-learning update, gets you further than all of these previous improvements combined. So this is pretty amazing. And you can look at the individual games. So here are 6 of them. So you can see the performance for basically doing this distributional Q-learning update with different numbers of bins. So C51 is shown in orange, and it's typically the best. But surprisingly, the gray curve shows distributional Q-learning with only 2 bins. So it's like reward 0 or reward 1. So even that often outperforms DQN. So switching from a regression update to essentially categorical update alone seems like a quite useful thing. So on some of these games, it gets close to, I think, essentially solving the game, getting the maximum possible score. So yeah, this was a huge advance. And particularly, I guess going back to the 2 directions I mentioned, the data efficiency is drastically improved here. So this is showing training, the amount of training data in millions of frames. And the orange curve shows sort of on how many games is DQN better than human after that amount of training. At least for this implementation of DQN. Then the blue curve shows the same for C51. So it surpasses the performance of DQN in like 40 million frames or less. So it's a very substantial improvement in data efficiency. Yeah, when you look at on how many games it's better than DQN, I guess here it's on 50 out of 57. So it's almost always better, which is not the case for some of the other improvements. So I guess one interesting bit about this work is it's actually still not clear why C51 works so well, which is pretty exciting. So is it the fact that we're learning a distribution? Is it the fact that you're sort of learning to model the uncertainty? Or is it really something about, I guess, so is it the auxiliary, using it as an auxiliary task, so having a richer signal to train your network, or do you really need a distribution to make the Bellman update work better? So there are still, many important questions to be answered. So that's the next one. So I guess, I should mention, so Unreal has much higher numbers here, but there is a little symbol showing that it was evaluated under a different setting. So in DQN, the standard is still to use fixed hyperparameters for all games. With policy gradient methods, which we find cheaper to run, and Unreal is a policy gradient method, we find that you can just tune the hyperparameters on each game separately. And when you do that, of course, you get better scores because, you're tuning it specifically for each game. But Yeah, we're going to look at that next in some detail. Okay, so again, DeepRL, as we've heard, is very data inefficient, and specifically on games with sparse rewards. So a game like Montezuma's Revenge, which many of you probably know about, is especially difficult. You have to control this character, navigate him through this maze, and you only get rewards for, say, like picking up a key or getting to the next room. And if you do anything wrong, you die. So it's a very difficult exploration problem because you can take millions of random actions and you get very few rewards. So what do you do when your problem has very sparse rewards? So it's probably like a very uncontroversial statement to say, well, you still get your input, so you should learn about the dynamics of the environment. You still see the character jumping around and how your actions affect the environment. So that has to be a very rich signal to learn from. So how can you do it? And that's the real question. In what form should you represent knowledge about the environment, and how do you learn it? So in some somewhat recent work, we looked at this idea of augmenting a reinforcement learning agent with auxiliary prediction and control tasks. And the idea here is by asking the agent to learn different things about the environment, it will help shape the representation of the neural network, and it should improve the data efficiency. So the agent I will describe is called Unreal, which stands for Unsupervised Reinforcement and Auxiliary Learning. Okay, so we've heard about policy gradient methods already. So Unreal takes an A3C agent. I guess the details are not that important. So you can take any reinforcement learning agent and ask it to answer extra prediction problems. So the basic setup is that we have our base agent, which happens to be a recurrent neural net, an LSTM-based agent, which outputs a value function and a policy at each time frame. And as it acts, we put all its experience into a replay buffer. And then offline, we can sample from this experience replay buffer and ask the agent to answer other prediction problems based on this data. And the idea is, okay, how can this help? Because if there are predictions that don't have anything to do with your actual task, how can it help? Well, the idea is that these prediction problems are answered using shared weights. So you share weights with the policy, and it will shape the representation of your agents and help you learn useful features faster. So we're going to quickly look at some of these other prediction tasks. So do I want to cover this? Right, so again, the idea here is that we only act using the base agent policy, and the rest of the stuff just helps shape the representation. So we add 3 specific auxiliary prediction problems. So the first one is adding what we call auxiliary control tasks. So the idea is to ask the agent to learn to perform many related tasks in its environment. And specifically, we're asking the agent to learn to control different aspects of its environment. And we looked at 2 kinds of problems. So one is we call pixel control. So the idea is you're going to look at your input, and you'll place some grid over it. So you'll break it up into a 20 by 20 grid or something like that. And for each cell in the grid, you're going to ask the agent to try and learn a policy that maximizes change in that part of the screen. So this seems like a funny thing to ask your agent to do, But the idea here is that knowing how your actions change the visual input is very basic knowledge that any agent essentially should be aware of. It's like if you move your hand in front of your eyes, you're not surprised by what's happening. You kind of know that, yeah, if you move your hand like this, that's where change will happen. So this is asking the agent to learn about low-level regularities in the visual input. And the idea is that these predictions hang off the agent's LSTM, and it shapes both the ConvNet, which helps it see, and the recurrent neural network, which helps it basically build up its state information over time. So we do this using Q-learning. So what's kind of cool here is that at every step now we have 400 rewards. So for each cell in the input, we can simply compute what the change was. And now we have 400 reinforcement learning problems that we're trying to solve. And because Q-learning is an off-policy learning method, we can just do Q-learning on all 400 reward signals at once. So the agent now is basically, learning to solve 400 other RL problems off policy. We looked at a variation of this called feature control, where instead of learning to control the visual input, you're learning to control features in your convolutional neural network. So here the idea is that the features of your network represent higher level knowledge about the environment, so slightly higher level visual concepts, and learning to control those might be more useful. So the second auxiliary prediction task, so it didn't work as well, but yeah, it's a very simple reason. So the second auxiliary prediction task was reward prediction. So here the idea was to sample a short trajectory of frames and to ask the agent to predict whether a rewarding transition will follow. So because this is an auxiliary prediction task, we're free to change the data distribution in any way we want. So in policy gradient, if you wanted to replay rewarding transitions more frequently, then you have to do off-policy learning, and you maybe want to do something like importance sampling corrections, and these kinds of things still don't, well, they can work well, but it's a bit more difficult. But here is just an auxiliary task that shapes your ConvNet. So because it doesn't directly influence your policy, you can choose any distribution you like. So what we ended up doing was sampling rewarding and non-rewarding transitions equally. So then in Montezuma's Revenge, if you, say, pick up the key once, you will replay this transition way more frequently. And you don't have to worry about off-policy learning. The last auxiliary prediction task was value function replay. So we would simply sample transitions from our replay buffer and update our value function more frequently than the policy. So this slightly accelerates the learning of the value function, which helps the agent pick up on features that are predictive of longer-term reward. I should have mentioned the reward prediction task. Because it focuses on short-term rewards, it helps you learn features predictive of short-term rewards faster. So overall, your three tasks basically help you learn visual features that help you control different aspects of the environment, visual features that are more predictive of short and long-term reward. And overall, this should give you a representation that makes it easier to solve the real task. So we tested this on a bunch of 3D environments from the DeepMind Lab, which is open source and everyone can use it. Probably not worth explaining all these curves, but the thing to look at is this is A3C training curve, where you have data on the x-axis and the average human normalized performance over 13 3D environments on the y-axis. And then you have Unreal. So you have essentially a 10-time improvement in data efficiency over just a vanilla reinforcement learning algorithm. So yeah, this I think is one of the really exciting things about RL. You can get a 10x improvement in your performance, and there's still lots of room. We need, multiple other 10x improvements to get to anything near human level speed of learning. And yeah, the other curves basically show that each of these auxiliary tasks helps on its own, but if you put them all together, that works even better. I might as well show the video. These videos are fun. So this will show basically the Unreal agent playing these tasks. So this is where you have to collect apples and avoid lemons. So this is pretty straightforward. This is a task where I think you have to suffer a small negative reward to get a big positive reward. These ones are more of these 3D maze navigation tasks where you have to try and remember the layout of the maze. There were a number of these of progressively larger sizes. So the maze levels are ones where Unreal accelerates learning a fair bit. So these are laser tag levels where you're playing against pre-programmed bots. Helps improve performance on these quite a bit too. And yeah, maybe we can skip this one. Right, so feature control. So feature control, I think, is a really exciting possibility, and I'm kind of sad that it doesn't work as well as it does. But I think this is, or as well as it should, but I think it's a really exciting direction, and there are more and more methods popping up that make some use of it. So again, in feature control, the idea is that you will learn policies for controlling the internal representation of your agent. So this is nice because it essentially helps you bootstrap learning. You don't pre-program sort of, which pixels you're trying to control. Your agent is learning to, collect rewards, so the features it's learning will be predictive of this reward. And then if you learn how to control these features, it should help you both learn faster. And also, I think the really exciting direction is it should help you discover useful behaviors. So if you're learning to pick up apples, maybe there is a feature predictive of how far you are from the apple. And then by doing feature control, you can learn policies that sort of help you efficiently move towards or away from an apple. And again, because your your internal representation sort of encodes all the aspects in the environment that you care about, by learning about all of them off policy, you're essentially learning to control all the relevant things about the environment at once, regardless of what the actual task is. So this idea does work in practice. So this is training curves on these on a random maze level, but pixel control was still always somehow slightly better. But I think, this is a potentially exciting direction for the future, which I'll mention again. Yes, so you can do both. You don't actually have to do these tasks offline. So specifically for pixel control, you can just unroll a trajectory and update everything at once, and then the gradients just get summed. But you can do it asynchronously too. It seems to work well enough. Okay, so model-based RL, I think you're going to hear more about it tomorrow, but this is an idea that I think a lot of people have been excited about, and there's huge promise in model-based RL. So yeah, why is there all this promise? So in the first lecture, Peter talked about sort of these exact methods for solving MDPs, and the reason we don't use them in practice for RL is because they assume that you have the dynamics of the environment and the reward function. But as I think someone asked in the questions, well, you can try and learn these dynamics. So if we could learn a model of the environment, then we can do a lot with it, because as we saw, if you have a model of the environment, you can learn the optimal value function, but you can actually evaluate any policy given a model of the environment. So this seems very, very powerful. But at the same time, it suggests that learning a model is hard. If it allows you to evaluate any policy using this model, that is surely harder than just evaluating just your own policy that you're following. So what are the different directions of model-based RL? So I think there are I would classify them into three different categories right now. So one is to look at explicit models, where you actually train something that takes state as input along with an action and produces the next state. So this is exactly the form of the dynamics we saw in the MDP. And you probably also want to learn the reward function. So you can train such a model. And neural networks are so good these days that you can actually learn very good simulators for Atari games and more complex environments. So I think for Atari, you can learn models that are essentially indistinguishable, and indistinguishable from the actual simulator when you predict things tens or hundreds of frames into the future. So then, why don't people use them? Well, it turns out that these models do have imperfections. And when you plug in an imperfect model into these planning methods, like say value iteration, they assume that you have the perfect model. And when you plug in an imperfect one, things can break down in bad ways. So in practice, I think in ridge domains, learning explicit models and plugging them into planners hasn't worked that well. But yeah, maybe that's changing. So another interesting direction is learning implicit environment models. So there are a couple of recent papers on this. So value iteration, that's from Tamar et al. Was, I think, best paper at NIPS. And the Predictron appeared at ICML this year. So here the idea is to look at the, I guess, mathematical structure of these planning algorithms and to embed the structure into your neural network architecture. And then the idea is you're still doing model-free RL, so maybe you're doing Q-learning or policy gradient, but you embed, your neural network is structured in a way that mimics the computations that a planner would do. And in many cases, this works really well. So it helps you learn much more efficiently on certain kinds of problems. But I think, again, as with explicit environment models, we haven't really seen this make massive improvements on sort of visually rich tasks, but yeah, again, maybe that's changing. So another even more recent development, I think, is this idea of interpreting imperfect explicit models. So there's this recent paper from DeepMind on imagination-augmented agents for deep RL from a few of my colleagues. And here the idea is that okay, we're going to learn a model of the environment, and we accept that this model will be imperfect. But we're not going to plug it into a planner that assumes a perfect model. What we will do is create these rollouts or imagined sequences from the model and give them to our agent as additional inputs. And then the agent can basically learn to do whatever it wants with them. So in this paper, the main task they looked at was Sokoban, which is a classic planning problem. It's interesting because in Sokoban, where you have to push these boxes into certain positions to get a reward, and they're irreversible decisions. So if you put a box into a corner, you can't pull it back out. So you make the problem unsolvable. So here what they did was for each action, they would imagine a trajectory. For each possible primitive action, you would imagine a trajectory that starts with that action. And then if you have k actions, you feed in these k trajectories into your agent. And there's a big neural network that looks at these imagined trajectories, compresses them into a single vector, and this goes into a standard model-free approach, say A3C in this case, I think. And this led to pretty big improvements on the Sokoban task. So I think this is nice because, it's a way to get around the fact that your model will be imperfect. These RL agents learn to use this information and get better performance on relatively difficult tasks. So I think model-based RL will be pretty important in the future, and I think it's still, again, another area that's wide open. Again, this is going to be especially important for cases where either you have a simulator that's really expensive or you want to do something in the real world, like on a robot, if you can't generate that much data in real time. Okay, so another cool model, I think, is this neural episodic controller. So most of the agents we've looked at so far are these neural net-based model-free methods. So they're parametric models, and learning is very slow. Basically, we make these SGD updates to the weights, and we need millions of updates usually, or millions or hundreds of thousands to get our models to do anything. So how can we learn more efficiently? So here the idea is that maybe we want a hybrid parametric, non-parametric system. So you can think of it intuitively as like a human has certain habits, so certain behaviors are ingrained, and you can perform them without thinking. So you can think of this as the parametric neural network. You do something many times, and then you can just do it while you're actively thinking about other stuff. And then the non-parametric aspect is when you really have to think, where you maybe recall certain experiences, like the first time you performed some sort of task, like, I don't know, riding a bicycle. You really have to think about it and to recall the experiences. So these are sort of not habitual. But humans are very good at making use of very little experience when basically using a different way of learning. So here the idea again is to build a model that tries to get the best of both worlds. So the idea now is we're going to have this non-parametric memory. So we're going to, for every piece of experience, we're going to put data into this key value store. So the key will be the representation, some encoding for this piece of experience or state that your neural network produced. And this bit is learned using gradient descent. So these keys are slowly changing, and it will take a long time, or it will take some amount of data to learn a good representation. But the values will be rapidly changing Q values. So for each state, you will essentially have some estimate of the Q value for its state. And the way these will be learned is much closer to tabular Q learning, where you specifically update a key value for one state. And this can be done faster than in a parametric model with weight sharing. And to produce an actual estimate for a state, so when you have to produce Q values for your current state, what you do is you look at your memory and you compare your current state to all the states in your key value store, and you find maybe the 50 most similar ones, and then you produce weights for these 50 most similar memories based on some kernel distance, and you take a weighted sum of the Q values in this store. So now, yeah, you have this slowly changing representation that you're learning for the keys, but you have these rapidly changing estimates for the Q values. And in practice, this can be much faster than purely parametric approaches. So these are learning curves on, I think, yeah, a couple of games, Miss Pac-Man and Pong, and we have sort of purely parametric approaches in the bottom, and then neural episodic control at the top. So again, I think this is a really exciting direction, but we still, yeah, there's still a lot of work to be done here. We don't know how to do these things very well yet. Okay, so I guess a few words about HRL. So hierarchical reinforcement learning is this idea that I think many people in deep RL have put a ton of time into because it's so intuitively appealing. But somehow it hasn't led to massive breakthroughs yet. So what is hierarchical reinforcement learning? Well, the idea is that, okay, convnets, we use convnets because we know there's structure in the visual inputs, but there's also structure in policy space. So when humans learn to perform some motor control tasks, we basically have some set of motor primitives that we use. Like once you learn how to control your arms and hands as a baby, you don't try to solve a new task by like randomly jittering your fingers. You perform exploration at a higher level of abstraction. You sort of know how to hold different objects and manipulate different parts of things. So the idea is to exploit the structure and policy space. So the Rich Sutton's work on options is a good example of this framework, where you have certain sub-policies that you might want to execute, which perform higher level actions. And then your overall policy might just select between these higher level actions. And what can this get you? Well, it can get you better exploration, and it can get you faster learning by reusing skills. So if you learn these options on one task, then you should be able to solve another task much more efficiently. So how do you actually do this in practice? So I think one of the more exciting pieces of work in HRL is this Feudal reinforcement learning idea from, the basic idea is from Diane and Hinton from 1993. So the idea is to decompose an agent into two levels. So there is now a manager and a worker. So the manager does not act in the environment directly. All the manager does is set goals for the worker. But the manager gets the reward from the environment for setting good goals. So it gets the true reward from the environment. Now the worker is who actually acts in the environment, but the worker gets rewarded only for achieving the goals set by the manager. The worker doesn't see the true goals or the true rewards from the environment. So why is this good? Well, one reason is that the worker basically has a much richer learning signal. If you have a very sparse reward problem, it might be hard to get any rewards. But whatever goal the manager set for the worker, you can always learn about that. Did you achieve it or did you fail to achieve it? So now you have this basically rich intrinsic reward signal. And the main issue, of course, is, well, how do you represent goals and how do you decide whether a goal has been achieved or not in a general enough way? And So this, yeah, maybe I'll skip to this slide. So there is, I think, a very practical instantiation of this in a paper by Sasha Vishnevitz and other colleagues from DeepMind, and the architecture is called Feudal networks. So the main idea is to represent goals in a shared feature space. So this relates somewhat to the feature control idea I mentioned. So here the manager outputs vectors in some shared feature space, and then the reward for the worker is essentially the cosine similarity between the worker's current state and this goal output by the manager. So this is very simple and I think very appealing intuitively. In practice, at least in this formulation, both the manager and the worker see some of the global reward, but the worker also gets this intrinsic reward based on how close the current state is to the goal set by the manager. And this is something that improves performance on a number of difficult exploration tasks, like say, Montezuma's Revenge. I guess, one quick example I can talk about is this task called water maze. So I think it's a classic task from neuroscience that rats are commonly trained on. So the idea is you have some sort of circular space and there is an invisible goal. And the first time the agent is placed in the environment, it has to explore and find the goal just by randomly walking around. But then you're placed into the same environment again, and the goal is in the same place. So then you are rewarded for going straight to the goal. So the Feudal network agent actually solves this task quite efficiently. So here we're shown the goal, and the different colors show different trajectories performed by the agent. So the green one is the first one, where it essentially moved around randomly until it stumbled onto the goal. And then you'd see that the other ones basically don't wander around randomly, but sometimes go straight to the goal or sometimes take a somewhat indirect path, but they do get there much faster. This circle on the right shows what these sub-goals actually look like. So each color shows a trajectory for a different sub-goal sampled from this featured space. So you see that the sub-goals that are learned are basically circular motions at some, or circular trajectories at some distance from the wall. So it doesn't learn the most efficient strategy, but it solves the task, which is quite difficult for a vanilla A3C agent. Right. So deep RL for real robots. I'm not going to say much about this because you're going to hear a lot more from people that have done great work on this. So Sergey Levine, Peter Abil, of course, Chelsea Finn. I think this is a really exciting area because it feels like either breakthroughs coming or it's already happening. It really feels like in the next few years, learning on robots will actually start to work well enough to have robots do really cool stuff in general environments. So how can we do this? All the methods we looked at are very data inefficient. So how can you do this on robots in a reasonable amount of time? And there are a couple of ideas. So one is basically learning in simulation, but doing transfer learning to reality. So the sim to real setting that people are looking at now. So how can you do this? Well, I guess one approach is to make your simulator look a lot like reality. And then first you train your agent in simulation where data is cheap. And then when you start learning in reality, you don't need as many trajectories to learn. So another paper from OpenAI of Tobin et al. Does it slightly differently, which yeah, I think this is a neat idea. So here in simulation, you actually assign render your scenes with crazy colors. So what this does is it encourages your network to really ignore low-level appearance when it doesn't matter. I think they were able to train an agent in simulation and then run it in reality, and it basically was able to solve some tasks without having trained on them in reality, which I think is exciting. The other direction is it seems like imitation learning will be important. So can we get robots to learn from human demonstrations much more efficiently? So this one-shot imitation learning paper from Rocky and others, I think, is really cool. So here, your policy, again, isn't just a parametric neural network that gets the current state. It does get the current state, which does go into the neural network, but you also maybe condition on a demonstration which tells you what the task is. So you can train this type of network on certain demonstrations, and it learns how to interpret the demonstration to perform the task. And then at test time, you can give it a demonstration of a task maybe it wasn't trained on. And you essentially learn from a single example. So yeah, I think, again, this area is wide open and there is a lot of exciting work to be done. So yeah, I think I'm just about out of time. So yeah, thanks for your attention. I'll take questions. Yep, Peter.
Any thoughts on exploration in
POMDP specifically.
related to feature control?
Yeah, so yeah, I'm a bit out of it, so thanks for. Yeah, I think feature control, the reason I'm really excited about feature control isn't just for improving data efficiency, but I think really making use of these learned behaviors should help us with exploration. So there is a recent paper from Imperial College London where they started doing hierarchical RL with pixel and feature control policies. And it's somewhat similar to these feudal nets, but it seems like, a relatively simple setup that works well on Montezuma and a few other difficult games. And yeah, maybe it seems like making use of uncertainty. Yeah, we don't quite know how to do that the right way yet. So either Bayesian approaches or maybe these distributional approaches, really making better use of uncertainty estimates, yeah, will be important. Yeah.
Feature control also seems to be trying to learn a lot about how states relate to one another. So how is it different from models that?
So yeah, people ask that. Yeah, that's a frequent question. In some way, it's very similar to a model. I think it gives you some of the benefits of a model, but it seems like it's easier to learn. So it's not as general as a model. We can't evaluate any policy. We're trying to learn an optimal policy for each specific feature. And yeah, it seems like we're not trying to predict pixels many frames into the future. So this idea of representing your prediction about the future as a value function of a feature. Value functions, we know a little bit about how to learn them, and they seem to be easier to learn than models. So I would say it's gets you part of the way there, but it's easier to learn. Yeah. Yeah, I mean, I think that's a really important area. I think, yeah, it's a really hard problem. I haven't worked on it myself, but if you want a really hard problem to solve, safety is one of them. Yeah.
You presented some very interesting algorithms, and you compared all of them with kind of like the baseline of the QN. I wonder how they compare with one another. Like, is one better than Unreal or vice versa?
Yeah, so I guess a lot of these improvements I think are orthogonal. So for example, yeah, there's no reason you can't add auxiliary tasks to like C51. So I think, yeah, that's one of the reasons why like we don't compare everything to everything else in every paper. It's more, yeah, if two things are sort of related, if they're competing with each other, then yeah, we should know which one is better. But when we're looking at somewhat orthogonal improvements, yeah, I think it would be interesting to see how well they combine. But yeah, many of these are orthogonal and should compound. Yeah. Oh yeah, so the question is, does the success of C51 basically imply that maybe assuming everything is Gaussian was bad? Yeah, I think, yeah, it might be slightly orthogonal to that. I think it does suggest that maybe training neural nets with like categorical losses is somehow inherently easier or more stable. You could, yeah, you could still apply some of these ideas to Gaussian distributions, like learn mixtures of Gaussians to learn like multimodal returns. So I don't think it's necessarily, yeah, a problem with assuming things are Gaussian. All right. Oh yeah, one more.
Yeah, I was wondering with the auxiliary tasks, is there going to be any success using supervised learning techniques like ladder networks in RL instead of defining manually like
Yeah, so oh, it's Peter. Is that a signal to? No. So yeah, I haven't seen applications of ladder nets. I think it would be cool. I had a slide which I cut where we looked at some basic unsupervised learning methods. Like, well, why don't we learn like an autoencoder on the inputs to shape the representation? And at least in our experiments, we found that like in these 3D environments, it initially accelerates learning, but then it kind of plateaus and maybe even hurts performance a little bit. And the reason is that basically, yeah, it doesn't take actions into account, and it's not at all informed by the reward. So in these like maze navigation tasks, it would learn to reconstruct the visual layout of the room quite well. But then because apples, like the rewards are rare, it would learn to like remove them. So it became blind. And it actually seemed like a signal that discouraged, like it fought with the RL signal about the importance of the apples, because they're rare, so it didn't care about reconstructing them that much. But it seems like, yeah, some sort of more classical unsupervised learning should help in some way. Maybe it's a matter of tuning. Yeah, I'm not sure. All right, yeah, I think.